So hello everyone, I'm Charles de Kergariou. So I'm going to present today my final conclusion of my PhD, sponsored by DSTL and called Design Process for 4D Printed Composite Agromorphic Bending Agromorphs, Microscopic Bending Agromorphs. So first question is, what is an agromorph? An agromorph is a structure that actuates when you immerse it in the relative, you change the relative humidity in which it is immersed. So this is the kind of structures that will bend when you change the humidity inside. So basically, these structures, as you can see, there is different patterns from the different layers of these structures. This is made of orthotropic materials, and therefore, when you have different patterns, the layers want to expand differentially. When you change the humidity, it is immersed in, which creates the bending actuations. So my PhD was looking basically at how the printing paths that we had for these structures influence the actuation we could get. So the first thing we did is measure the quality of the material. So we measure the porosity of the material I presented 2 years ago in the Symposium. Then we look at the influence of humidity on the stiffness, because the stiffness influences the actuation, and humidity therefore influences the actuation. I presented last year at the Symposium, and like all amazing trilogies, there is a third episode. It's upon us today. It's the design process, and it's called The Return of the Flax Fiber. Anyway, so the broad context of my PhD talks about 4D printing, especially of composite materials, of 3D printing, relative humidity, so RH, which is relative humidity, and bending actuations. There are other parameters which could be considered: assembly technique, environment to immerse your specimen in, and actuation, but we only focus on this one. And the first thing that we wanted to do is design a design guide, basically, which goes through all the different design space you need to go through to design a 4D printed structures, in order to see, to propose it to the greater public. And that's what we did, and we published it in Advanced Functional Material. Basically, we went from conceptual design of agromorphs, and we went to printing, conditioning, and measuring the actuation of the specimen. We discussed about material, about structures, about how do you optimize it, how do you design it. And all the different steps are well described in this design guide. If you're interested in 4D printed agromorphs, you can have a look to this one. We also use this design guide for our own specific material, which is continuous flax fiber reinforced polylactic acid. And the first thing we wanted to do is producing this material is fairly constraining in terms of the printer that we're using. And therefore, we wanted to create a model which is capable of modeling that kind of structures. And that's what we did. We created a model based on the G-code. So the G-code you use for printing, we turn it into images. And these images we use to obtain the parameter we need to obtain the FEA model. And we wanted a validation system for FEA model. What we did is one day I was walking in the park. I saw a beautiful tree with nice flat leaves. So that's an example of a leaf. And on the ground, there were some dry leaves, which are doubly curved. And so we tried to look at what are the patterns of the veins on the leaf and try to reproduce it. So that's the G-code we used on the right side of the screen, which reproduce the vein patterns on the leaf and try to mimic these B curvature structures. So we printed the specimen, we conditioned it, and we measure this deformation. So these are DIC results for these specimens. The flat layer is a dry specimen, and the curved one is 98% relative humidity conditioned specimen. You can see that we are able to achieve the two different curvatures. So K2B and K1B are the two curvatures that are obtained for the B curvature structures. And we compare to our FEA model. We obtain good qualitative comparison in terms of shape and in terms of order of magnitude of deformations. And in the paper we published, we discuss the differences that we've been able to observe, but also the lack of repeatability that we observe for our structures. Measurements. So then we went to different structures. So this is a photo of a Kaya lily, trying to mimic the Kaya lily shape, which is known in 4D printing structures for its double curvature, but anticlastic curvature, and also the large amplitude. We tried to mimic it. It was a bit more complex than the previous one because we could not obtain enough amplitude to do this, and therefore we decided to explore the design space a bit more by looking at simpler specimen. Here an example of a specimen which has a 90 degrees plus or minus alpha stacking sequence. We vary the angle of alpha and look at the angle of alpha that gave the best amplitude, the largest amplitude, which is around 40 and 50% angle. And so that's different tests that this is an example of different tests that we've been conducted in my PhD to explore this design space. And you can find in the paper that we published. Thank you very much for your attention. I hope you enjoy this presentation.
Go.